So as you can see, the title of this talk is Computer Simulations in Conceptual Engineering. So in a previous paper, I defended a particular application of explication, which I called conceptual clarification. I'll talk very briefly about that today, but I defended the use of experimental cognitive psychological methods as a sort of external tool and scientific tool for evaluating and improving our concept clarification, concept clarifying explications. In this talk, I want to talk about computer simulations as a useful empirical, if you will, scientific analytic tool for improving and developing our concept engineering explications. So here's the plan for the talk. I want to start by just sort of having us all remember the modern beginnings of explication. I'm going to very briefly talk about Carnap on explication, at which point we'll talk about different uses of explication, and then we'll focus in specifically on what I call concept engineering. So by that, I mean my particular view on what concept engineering is. There's this odd menu item here, lessons from a toothbrush factory. I'll have to explain that when we get there. But truly, I will be drawing some lessons that I learned while working in a toothbrush factory into this talk. So, and then for the second half of the talk, we'll be talking about a particular case study of concept engineering and how I've used computer simulations in that particular case. And I want to basically bring these lessons from the toothbrush factory into philosophical practice and show how they show up and are useful when it comes to explicating epistemically, especially epistemically important concepts like explanatorinness. Okay, so there's the plan. On to part one. So again, let's start with just remembering what Carnap said about explication. I think this will be helpful for us to set the stage for where I want to take this today. Carnap, in his chapter 1 on explication of his logical foundations of probability, writes this: explication consists in transforming a given more or less inexact concept into an exact one, or rather in replacing the first by the second. We call the given concept the explicandum, and the exact concept proposed to take the place of the first the explicatum. The explicandum may belong to everyday language or to a previous stage in the development of scientific language. The explicatum must be given by explicit rules for its use, for example, by a definition which incorporates it into a well-constructed system of scientific, either logical, mathematical, or empirical concepts. Now, of course, there's Carnap's sort of encapsulation of what he means by explication. And he specifically sets this off and contrasts it with what he calls the procedure of analysis. So, of course, here he's talking about something like ordinary language, ordinary language conceptual analysis. And what he says is, this can't be analysis. This method of explication can't really be identified with the procedure of analysis because the explicandum is more or less vague, and certainly more so than the explicatum. By virtue of the very nature of the method, the explicatum has to be more precise, more exact than the explicandum. And so it's obvious that we cannot require the correspondence between the two concepts to be a complete coincidence. Okay, this is all review. But at this point, I want to really focus in on that, because by discarding or by setting the method of explication off against the procedure of analysis, what Carnap effectively does is now presents the need for new criteria of success, right? With the procedure of analysis, we have a very clear sense of what it takes to have a, so to speak, an accurate or correct, satisfactory, adequate analysis. And it's exactly that requirement of complete coincidence. As explication parts ways with analysis, there goes the perfectly clear criterion for success, so to speak, right? So Carnap goes on then, understandably, in the very next section of this chapter to develop his desiderata for a satisfactory explication. Okay. The first one's similarity, and I'll be quoting Carnap for each of these 4 desiderata. So you'll get to see what Carnap himself said explicitly about what he means by these things. But then with regards to some of these desiderata will part ways from Carnap. Okay, so similarity, Carnap writes, in most cases in which the explicandum has so far been used, the explicatum can be used. However, close similarity is not required, and considerable differences are permitted. So, of course, this is where he's explicitly parting ways from the criteria of success for analysis. We don't require complete identity or perfect overlap, so to speak. We rather require just some degree of similarity, and indeed, close similarity is not even required. So why would we ever want to part ways drastically or radically from our explicandum when giving an explication? Of course, Carnap's already sort of showing his cards here. He wants to use explication for concept engineering or something like that. And so he's not so worried about similarity. This is not Carnap's most important desideratum. Desideratum 2 is the exactness desideratum. So Carnap writes, the explicatum must be given by explicit rules for its use. For example, by a definition which incorporates it into a well-constructed system of scientific, either logical, mathematical, or empirical concepts. Okay. Elsewhere, Carnap writes, at the very least, all that we're requiring here is that the explicatum has to be more precise in some very pragmatic sense than the explicandum. There has to be an improvement in precision or exactness. Now, fruitfulness gets an asterisk here because I think Carnap has a particularly idiosyncratic, special sense of fruitfulness in mind, which he clarifies here. He says the explicatum has to be useful for the formulation of many universal statements, that is, empirical laws in the case of a non-logical concept, or logical theorems in the case of a logical concept. And that's the exact sense of fruitfulness that Carnap has in mind. He never gives an official, if you will, explication of fruitfulness itself. But his thoughts on fruitfulness, as conveyed, for example, here, effectively act like an explication. I think he understands that this is not an analysis of what we mean by fruitfulness generally, but he's rather explicating fruitfulness. By fruitfulness, he has in mind very specifically and precisely that the explicatum is to be useful for the formulation of generalities, for theorems or laws. More on that in a bit. And then finally, the fourth desideratum's simplicity. And Carnap says the least about this requirement. He does seem to, in his examples, he seems to sort of convey the idea that simplicity is something we evaluate not only in the statement of the explicatum, but also in the statement of the laws that we can derive using the explicatum. So both of those are, simplicity is determined by both of those things. Notice his statement here, which is one of the first and only things he says explicitly about simplicity, seems to sort of give, if you will, lexical inferiority to simplicity over the others, right? Simplicity is only important insofar as the other three criteria don't already tell us what explicata to prefer. Okay, now these desiderata, of course, don't always play nicely with one another. You often have to choose how to balance these against one another, how to trade them off against one another. So the next question is how to do that. Does Carnap give us much insight with respect to how to balance these desiderata? And the answer is no, not very much insight at all, at least not explicitly. However, in practice, in Carnap's examples, and in his use of explication in his actual philosophical practice, it seems clear that Carnap, at the very least, wants to give fruitfulness, asterisk, lexical priority over similarity. So we see this, for example, in Carnap's History of Thermodynamics example, one of the two key scientific examples of explication he gives in that chapter of his book. He says, it would be possible, but highly inadvisable to define a concept temperature in such a way that X and Y are said to have the same temperature whenever our sensations do not show a difference. This concept would be in closer agreement with, that is more similar to, the explicandum than the concept temperature actually used. But, and here comes the important comment, the latter has the advantage of much greater simplicity, both in its definition, in other words, in its method of measurement, and in the laws formulated with its help. So notice already here, it's unclear exactly how Carnap's ranking these things. What is clear is that he likes fruitfulness a lot. What is not clear is how he ranks fruitfulness against, how he ranks here similarity against, for example, simplicity. So before it seemed to be the case that he was giving simplicity lexical inferiority under all the other criteria. Here he seems to be suggesting that sometimes we might want to give up on some degree of similarity, not just for the sake of fruitfulness, but also for the sake of, as he puts it here, simplicity in definition. Anyway, so that's just to say it's not at all clear how Carnap ranks these things, but it does seem clear that Carnap ranks fruitfulness pretty consistently higher than any of the other desiderata. Okay, this is also the fact that Carnap ranks fruitfulness so highly is also pretty clear in just his general philosophical outlook and his general philosophical pragmatism. So there's a lovely quote. Here's a lovely quote by Richard Jeffrey. Jeffrey says, philosophically, Carnap was a social democrat. His ideals were those of the Enlightenment. His persistent central idea was, it's high time we took charge of our own mental lives, time to engineer our own conceptual scheme as best we can to serve our own purposes, time to take it back from tradition, to choose our purposes and concepts to serve those purposes, if indeed we are to choose those things and not simply suffer them. Yeah. Notice already here a more general idea of fruitfulness than Carnap's is automatically coming out in Jeffrey's own thoughts. So here Jeffrey talks about engineering conceptual scheme in order to serve our purposes, and not necessarily talking about our purposes being the statement of general laws and logical theorems. So there's sort of an easy move to get beyond Carnap's own idiosyncratic thoughts on explication waiting here for us, and that is to think of fruitfulness more broadly than Carnap himself thought of fruitfulness. Okay, so if we want to sort of use explication beyond the ways that Carnap himself used it, and to define other useful ways to use this general method, that does give us one potential move to make. We can think of fruitfulness in a more general way, and that's kind of the easy and obvious move to make. We don't always just want to develop explicata that are going to be able to, where the sort of high mark of success is going to be their ability to give us, or them giving us the ability to state general theorems or laws. Although that's sometimes what we want to develop explicata to do for us. So instead of using that asterisk now, I will just talk about fruitfulness as a desideratum more generally, where we're talking about something like, and typically actually inevitably in this talk across the board, I'll be talking about an epistemic sense of fruitfulness, where we lay down sort of epistemic goals and epistemic ends we have, and we talk about the fruitfulness of an explicatum as that concept's ability to allow us to achieve those specific epistemic ends. So if we let this symbol here, I assume you can see my cursor, if we let that denote lexical priority, then another move we can make to go beyond Carnap in defining other uses for explication is to let different weighting schema. So instead of thinking there's sort of one right way, as Carnap seems to imply in practice and in his general philosophical outlook, as opposed to thinking there's just one right way to weight these desiderata against one another, we might instead see if we can get more mileage out of the general method by considering whether other projects could be served by weighting those desiderata in different ways against one another. And this goes to a comment I've made in a paper on this topic, where I suggested that there are at least two important explicative projects awaiting us, and it sort of made possible by weighting these explicata against one another in distinct ways. So first we have concept engineering, and here's how I think of concept engineering. I think of concept engineering as the explicative method where fruitfulness is given lexical priority over similarity and exactness. Similarity and exactness can sort of fight against one another on the next level of priority, and simplicity's ranked. Just here, I'm just following Carnap, at least in what he says explicitly about this, where simplicity only has a say if the other three desiderata don't tell us what to prefer. So here with concept engineering, again, the way I think of this is that the focus is on the explicatum itself. The focus is really on that newly engineered concept. And the overarching goal that we have is to part from the explicatum in ways that will improve our epistemic lots when thinking or researching in terms of that new concept, in terms of the explicatum. Really, and you can only do that, of course, you can only make improvements if the explicatum parts from the explicatum. And so really a parting of the ways between these concepts is truly necessary in order to be engineering a new concept, of course, and in order to gain increases in fruitfulness. So that's the way I think of concept engineering. But we could also weight these desiderata against one another in a different way. For example, here's one other way we could do it. We could put fruitfulness sort of second in rank, where similarity and exactness can sort of fight it out with each other at a level of lexical priority above fruitfulness. Now, why would you want to do that? Well, formal epistemologists, for example, do this all the time. The idea is to try to shed light on some concept we use in our everyday epistemic lives by exploring exploring the implications of a much more precise version of a concept that nonetheless retains a deep degree of similarity to that everyday concept, right? So here the focus is on the explicandum, and the overarching goal here is to illuminate rather than to replace this concept, the explicandum, by the study of an associated, and it has to remain associated. It has to remain very similar, but more precise concept, where the increase in precision allows us to get sort of more of an analytic handle on the normative, for example, the normative or epistemic upshot of this concept. But because it retains such a deep degree of similarity to the original concept, we're still arguably shedding light on how that concept functions for us in our everyday lives. That's the idea. This is concept engineering versus concept clarification. Of course, for the sake of this talk, I'm going to focus on concept engineering. Okay. Now, concept engineering, it's sort of easy to come up with examples of concept engineering in philosophy today. And most of these come either in logic, in the form of logic, or in the philosophies of the special sciences. And I think that's because, right, the whole idea here is we're supposed to be engineering a new concept that's going to be, at least again, the way I'm thinking about this for the sake of the talk, fruitful to satisfying some epistemic ends we have. And so when we develop a new logic, for example, we're hoping that this logic is truly guiding our reasoning in ways that allow us to satisfy such epistemic ends. Similarly, when we're doing the philosophy of the special sciences, we're often interested in developing new concepts that will advance those sciences and that will allow those sciences to work more efficiently and make discoveries more efficiently and more accurately, right? So at least that's the idea. So Philip Kitcher, for example, writes, when he's talking about concept engineering in philosophy of biology in particular, there's no higher standard to which our concepts are to answer than the efficient satisfaction of the purposes of inquiry. The task of projects in philosophy of biology that focus on concepts like gene and species is then to provide exact reconstructions of notions that are useful for the current purposes of inquiry. And we see a bunch of examples in the philosophy of biology where people are explicitly interested in engineering new versions of concepts. They're not very interested in worrying about similarity, the similarity of their new concepts to the old concepts. They're far more interested in seeing what the fruitfulness, the potential fruitfulness for the sake of biological practice would be of adopting these new conceptual schema. And there's a bunch of examples there of work within the last few decades doing exactly what I just described. But logics themselves, according to Carnap, can be thought of as sort of grand experimentations in explication, right? Grand exercises in explication. So this is true, according to Carnap, both on the metalogical level and within logics. So first of all, on the metalogical level, you might think of a particular logic as giving us a way to explicate notions like logical truth, logical falsity, implication, entailment, synonymy, etc. So Carnap himself writes L implication, which is the name he gives to his particular precise explication of implication of the everyday, or the less precise notion of implication. He says L implications are explication for the traditional, so-called traditional concept, which is usually called implication or logical implication or entailment, and whose inverse is ordinarily referred to by such terms as logical consequence, deducibility, and the like. But we can also think of logics as involving explications, not just allowing us to do explications on the metalogical level, but involving explications within themselves, within their own language, right? So you can think, for example, of the formal connectives in this way. So, right, the wedge here, for example, can be thought of as once it's given a formal semantics and once interpreted as an explication of the function of conjunction in everyday language, right? To use Hannes Leikeb's phrase from a couple weeks ago, the wedge can be thought of as an explication of the sort of merely expressive idea of conjunction. Yeah. Okay, so I'll just say really briefly. This is kind of beside the point, but I thought it was interesting. Of course, even across these two different uses of explication for logics, you might think that they differ in their very purpose. So you might think, for example, that the metalogical concepts and our explication of them should be pursued for concept engineering's sake, right? To allow us to achieve our epistemic ends using the logical language in a way that sort of improves our epistemic performance. At the same time, as thinking of that, you might think that our explications within the logical language should retain a great degree of similarity to the everyday sort of concepts they're supposed to be explicating, and thus that the explication constituted by, for example, our formal semantics of the wedge should be pursued for concept clarification of conjunction. Right. So you might think that the purposes of the explications here are different, and it makes a great deal of difference, right? Because, for example, is the material conditional an adequate explication? It's a really good question. Those who argue that it's clearly not typically think that for reasons that betray that they think of the explication here as intended for concept clarification. Right, the material conditional parts ways drastically, radically from our everyday notion of conditionality as expressed by if-then. So clearly fails similarity, or at least there's very good reasons for thinking so. On the other hand, if you think that the material conditional is there for explication a la concept engineering, there's a much better case potentially to be made for adopting the material conditional. So especially when combined with considerations of precision. So if you want a bivalent, binary, truth functional explication of if-then, and if you also want fruitfulness, in this case, something like Carnap sense, where you want to be able to give grounding for these three different generalizations, these metalogical theorems or generalities. So if phi then psi is false, if phi is true and psi is false, affirming the consequent is invalid, and if phi then phi is true, whether phi is true or false. If you'd like to have an explication that grounds all three of those generalities, while also having precision in the sense of bivalence and binary truth functional connectives, then this is the only way for you, right? This is the only explicatum that would be acceptable to you. So again, if we're in this for concept engineering sake and not concept clarification sake, the arguments against material conditional are not so clear and compelling anymore, necessarily. Yeah, I should hurry through this slide. So Beall and Restall, their work on logical pluralism can also be thought of as endorsing logics as concept engineering explications. So of course, they think of logics as being explications of logical consequence, and where the patterns of these explicata, of potential explicata, is the generalized Tarski thesis, where we say an argument is valid sub x if and only if in every case sub x in which the premises are true, so is the conclusion. And you get different admissible explicata And this is their pluralist thesis. You get different logics, in other words, that serve as explications of logical consequence by treating and explicating that idea of case differently. Cases as Tarskian models or possible worlds gives you classical logic, situations gives you relevant logic, irrelevant logic, and cases as stages and constructions gives you an intuitionistic logic. Right. The important point here is that they accept all of these as good explications of logical consequence, exactly for concept engineering sort of reasons, exactly because they serve different fruitful ends, right? They serve different epistemic ends fruitfully. So classical consequence, they say, keeps us from stepping from truth to falsehood, period, across the board. Whereas the intuitionistic consequence takes us from truth to truths within constructions. And here they write, classical consequence does not do every job required of deductive validity. Other logics are better suited to some of these tasks, and that's why we need a plurality of logics. Okay. So the focus here is on concept engineering. And now I want to start making my way into the discussion of computer simulations and how they can inform our concept engineering explications. So in order to do concept engineering, in order to do it, I think, well and efficiently, we of course need some way to gauge fruitfulness. Okay. And here's where we get some lessons that we can learn from a toothbrush factory. So here I did an engineering degree as an undergraduate degree, and then I worked for a couple of years at Oral-B Laboratories, literally redesigning floor layouts for assembly lines for toothbrushes. And so that was my task. I was supposed to be designing different ways of laying out the factory floor in order to increase efficiency. That's what I was worried about for a couple of years of my life. So here are some lessons that I learned from that experience that I think we can relate to engineering more generally, and indeed concept engineering. So in engineering a new factory floor layout, importantly, one doesn't wait until the new design has been implemented to test its fruitfulness. Yeah, that is, you don't sort of test the fruitfulness of potential layouts by actually implementing the layout, redesigning the whole factory floor, and then seeing how it goes. There's got to be ways that you have of testing fruitfulness before actually having to physically implement the design. Otherwise, it's too costly. It can be costly in terms of production if things don't work out according to how you think they might, according to the new design. But also, it's costly to take the time to redesign the floor. And if you have to do this multiple times because things aren't working out in terms of efficiency and fruitfulness, then it gets very costly. So you don't want to do that. You don't want to have to wait until the new design has been implemented to test its fruitfulness. So what do you do instead? Instead, you virtually implement the design as accurately as you possibly can, but virtually. And so the way that we were doing this is you used AutoCAD, and you represented as accurately as possible on the computer your new floor layout and design. Then using that, you simulated the working of the factory with the new design. And here, sometimes this was done on paper with systems of equations and calculations. Sometimes it was done on computers with computer simulations. But this gave you some way in the office of gauging and evaluating, estimating what the fruitfulness or the efficiency of this new floor layout would be. So this provides an estimate of the design's fruitfulness. Now, importantly, all of this becomes part it becomes part of the engineering process itself. Because you get this feedback loop, right? What ends up happening is you experiment with the layout using this virtual means, and then you see what the estimated fruitfulness of that layout would be. And then you let that inform ways you might alter that layout to even sort of continue to ratchet up the potential efficiency of floor layouts. And you keep ratcheting this up, you keep trying out new potential designs until you're satisfied that you've pretty well optimized efficiency, and then you can implement the design, Of course, the experimentation, what sort of different possible layouts you're trying out, and experimenting with is not just blind. It's not just a blind process. That would also become way too costly if you just did this randomly and blindly. Instead, you let pre-designed theories of optimization and floor layouts and the experience of other factories, for example, inform how you experiment, what directions you experiment in with the layout so that you can eventually optimize the fruitfulness of the new floor design. Okay, now I think these lessons are worth considering for conceptual engineering too. I think they all carry over in very nice, seamless, and interesting ways to the cases where we're engineering not floor layouts, but concepts. Okay. So here's how we can change things. In engineering a new concept, we might say, one doesn't want to wait until the new design's been implemented to test its fruitfulness. That can also be costly, especially, for example, take the example where you're trying to engineer a new statistical concept, a concept for statistical testing. The worst idea you could have is to try to teach statisticians and practicing statisticians and working scientists this new statistical concept and then just see how it works out in terms of fruitfulness. No, of course, that would be a bad idea. You want some way of gauging what the fruitfulness would be of the new statistical concept before you put the cost in and the effort to try to educate working statisticians and scientists on how to apply this concept. And of course, fruitfulness here is a more general concept. We're talking about fruitfulness apropos some desired end. Okay. So in order to do that, in order to try to come up with a means of testing the fruitfulness of a concept, you provisionally explicate the concept as accurately as possible. And notice by accurately, I do, in part at least, mean taking into account considerations of similarity. That's part of what will inform, instead of doing this blindly, that's part of what will inform the process of which directions to potentially alter concepts in or change concepts or introduce new concepts that you think are worthy of being tested in terms of their potential fruitfulness. But these are all provisional. You have a bunch of provisional explicata. After that, you then simulate the so-called factory. I'll still keep that phrase. Then you might say what the factory is. It depends on what the explicatum is supposed to be for. This could be the reasoning process in terms of, and in the example I'll give, this will be something like the reasoning process for theoretical reasoning in the face of uncertainty in the sciences. But we want to simulate the factory using the new explicatum, and this provides an estimate of the explicatum's fruitfulness, that new concept's fruitfulness. Now, this process becomes part of the design engineering process itself. We can allow that to happen, and that's a good thing. We can allow this sort of simulation and testing, virtual testing of explicata and their potential fruitfulnesses to inform our engineering process itself. We can experiment with provisional, very different and distinct provisional explicata, iterating that above process in order to continue to ratchet up the potential fruitfulness of a new explicatum. Until at the end of that process, we've decided that we've pretty well optimized our concept and we're ready to put the cost in, at least to the extent where we're happy to and comfortable spending the cost that it will take to implement the new concept, wherever it needs to be implemented. This experimentation is not random, as I've already hinted at, but directed by pre-designed theories. For example, theories about the desired end and what it would take to reach that desired end, but also similarities involved here. So notice we're getting a more subtle and more nuanced take of how these desiderata might relate to one another in this process than Carnap's simple fruitfulness takes and swamps all sort of picture. Here, similarity itself is having a role in what ideas get tested for fruitfulness in the first place. So those are the basic ideas. I think all of this becomes much clearer if you look at a specific example. So what I want to do now is look at my case study, Explicating Explanatoriness, some of the work I've done using explication, and this work specifically on, as you've seen, the notion of explanatoriness and using explanatory inductive logical considerations to try to give us a criterion for choice of theory. When we're making choices when we're in theory choice sort of tasks where we're trying to figure out which theories we might prefer. Okay. I'm going to go rather quickly through the setup here now. The Peircean explanandum for the notion of explanatoriness I have in mind is famously given in this quote. I'm going to return to the important part of this quote in a second. So I'm going to skip over this for now, and I'll return to it in a second. Peirce here makes very clear that what we're talking about when we talk about explanatoriness is something like the epistemic function of that explanations often have for us and for reasoners, not the nature of explanation itself. What we're interested in doing here when we're explicating explanatoriness is not trying to give a new account of what it takes for to have an explanation, but we're trying to give an account of what the epistemic effects of explanations tends to be. So he says, we notice a plant that is flagging on a hot summer day. The next morning it stands up again, fresh and green. Why has it revived in the morning? Oh, they always do. Of course, that's not an explication. That's not an explanation, right? So Peirce continues, he says, one may smile at the naivety of this. Certainly it's not an explanation in the proper sense of the word. Still, its general function is the same as that of an explanation. It renders the fact a conclusion necessary or probable from what is already well known. Okay, so we're getting an idea of what this function is supposed to be when we have explanations. The idea is something like this. Actually, I'll go back to this slide now and refer to this. You have some surprising fact E that's observed, and if this potential explanation for it is true, then E would be a matter of course, and so there's thus reason to suspect that H is true. The idea, again, is that explanatoriness, the epistemic function that explanations tend to have on us, is they make some explanandum. Notice there's no other terminology to use here, but I'm not saying explicandum, but explanandum, the thing to be explained. They make that explanandum E more expected, right? To the extent that an H is explanatory of some E, it makes E more expected. So informally, if we were to give a sort of informal description of what the explicandum is now that we're interested in explicating, it's this: explanatoriness in the sense of the epistemic function that explanations tend to serve by virtue of rendering explananda more expected for us, increasing the degree to which we would expect this fact that needs explaining to be true. So there's that quote again. The idea of abductive inference in Peirce's language, or explanatory inference, is this: we have some surprising fact E, but if H were true, E would be a matter of course. Hence, there's reason to suspect that H is true. This invites this probabilistic reading. Suffice it to say, the most important point I want to make on this slide is that if you want to give a probabilistic explication of explanatoriness in this basic Peircean sense, then it invites measures of explanatoriness, measures of explanatoriness that are sort of measures of this inequality. Right? And that makes sense, right? We have the surprising fact E is observed, so and then if H were true, E would be a matter of course. So the notion of explanatoriness here again is something like E is made much more expected in light of H than it otherwise was. And in terms of Bayesian interpreted probabilities, that's captured by this inequality. And to the extent that this inequality holds, the strength of that inequality itself gives us a sort of measure of the degree of explanatoriness that some H has over an E. That's the basic idea. Now, how to make that more precise, how to actually give a measure or a quantitative explication of this idea of explanatoriness? Well, it's been tried in many different ways. So here's three. So I.J. Good and Timothy McGrew more recently offered this measure, which is sort of the most transparently appropriate measure of what we're after, because remember, we just want to measure of how much greater this term is than this term. Popper gives a similar measure. In fact, Popper's measure here is ordinally equivalent to this measure. In work that I've done with Jan Springer and on my own, I propose and defend this measure. This one doesn't look necessarily like it would be a measure of the inequality between this term and this term, but it is. It's measuring exactly that. It's just not so formally transparent in the statement of the measure. Okay. All of these, we don't have to choose between these. All of these have the following theorem in common. So for fixed E, and any two distinct potentially explanatory hypotheses, HI and HJ, inequalities in the degree of explanatoriness according to any of these three measures basically just reduces to inequalities in likelihoods. Okay, so the most explanatory theory H over some E is thereby also that reduces to the judgment that hypothesis has the greatest likelihood with respect to that evidence. The probability of the evidence on that hypothesis is greater than it is on any other hypothesis. Now, that theorem itself is a reason why you might want to call that idea into question. You might think explanatoriness should not be explicated just merely as a measure of that inequality. Because after all, Peirce, in a quote we've already given, says this: its general function is the same as that of explanation. So what's the function of explanation? What is this idea of explanatoriness? It renders the fact a conclusion, necessary or probable. That's that idea of the explanandum becoming more expected, necessary or probable in light of the H. But then it says, from what is already well known. So there's also this idea that maybe we should also take into account how plausible the potential explanation itself is, apart from considerations of the evidence. We want to be able to explain evidence in the sense of increases expectedness, but by referring to some hypothesis that's already somewhat plausible for us, ideally. That's the idea. So Gleamore offers this idea, which is just to say nothing more or less than that the posterior probability of a hypothesis, the probability that a hypothesis has conditional on the evidence, is what we mean by explanatoriness. And the fact that this sort of accommodates this sort of intuition, that Gleamore's idea accommodates this sort of intuition here, is made more apparent by the fact that we can write posterior probability as the product of the prior probability of a hypothesis and its measure of explanatoriness according to the Good and McGrew measure on the previous screen. So this, if we think that explanatoriness amounts to a posterior probability, the probability of a hypothesis conditional on the evidence, what we're effectively saying is that not only is explanatoriness a matter of how much you're able to sort of render the explanandum more expected, increase the expectedness of the explanandum, but it's also a matter of this term, how expected that hypothesis is in the first place. Or in other words, how probable that hypothesis is in the first place, whether it's, and the extent to which it's already well known, to use Peirce's phrase. All right. So now we want to, what we want to do now, the reason I took some time doing that, right, is, and now I want to look at these potential, we got a bunch of different potential explicata. Now, effectively, we really just have two, because we have the one that says that differences in explanatoriness for different hypotheses with respect to the same evidence amount to likelihood comparisons. That's a formal explication in the inductive logic of probability theory of explanatoriness. And then we have this idea instead that in that same sort of precise, exact formal system, the system of probability theory, explanatoriness should be explicated not just as differences in likelihood, but differences in likelihood combined with differences in prior plausibility or prior probabilities. Now what we want to do is see whether computer simulations could start giving us insight here, right? Giving us insight here into the engineering process, not only in comparing the potential fruitfulness of these different explicata, these two different explicata now on the table, but also in hopefully giving us more guidance in developing more explicata beside those that maybe improve on both of them. Okay, that's the idea. So what is the end we want to serve here? Well, just to cite Peirce again, remember, Peirce wants us to be able to use this sort of considerations of explanatoryness to gain reason to believe things are true. That's his phrase. In other words, what we really love is a super fruitful explicatum corresponding to the informal notion of explanatoriness that gives us a great criterion for theory choice that allows us, that sort of lands us in the truth, that allows us to pick true theories, at least to some degree. And to the extent it's able to do that, it's fruitful. That's the notion of fruitfulness in mind here. Favoring true theories, something like that. Okay, so here's how here's the first round of computer simulations. Here's how I developed these. Here's how I designed these computer simulations. Remember, the idea is to compare the sort of success rates, if you will, at hitting on the truth of these two different explicata. So step one, I have the computer for a specified number n of competing explanatory hypotheses. I have the computer randomly assign priors and likelihoods to those hypotheses. Step two, using the respective values of the prior probabilities, the respective probabilities of the hypotheses, the computer stochastically randomly selects the true hypothesis, I'm going to call that Hj, from the n different alternatives. By stochastically randomly, what I mean is, for example, if the computer randomly assigned a 0.4 probability to H1, let's say, then at this stage, and let's say also a 0.1 probability to H2, then H1 truly has 4 times the chance of being randomly selected as the true hypothesis than H2 in step 2. Does that make sense? It's stochastic. It's random, but it's depending on the particular prior distribution that was assigned in step 1. Step 3, we use the value of the probability of E given Hj. Remember, Hj is that randomly selected true hypothesis. So we use the likelihood associated with the true hypothesis to check whether E occurs. If E doesn't occur, that is, if E is not true, if it's not randomly selected as true according to this likelihood, in line with this likelihood, then this iteration of the simulation is over. If E does occur, then we continue to the next 3 steps. So step 4, we check which of the n hypotheses has the greatest explanatoriness, which is another way of saying, remember, which one has the greatest likelihood for that evidence? Which one assigns the greatest probability for that evidence? And we call that HK. So HK is now, Hj is the true hypothesis. HK is the hypothesis with the greatest explanatoriness according to these E explications of explanatoriness. Step 5, we do the Gleamore thing. We check which of the n hypotheses is the most probable in light of E. That is, we just look at which one has the greatest posterior probability on E. And we'll call that HL. And then finally, step 6, all we do now is just compare and count. So if HK equals Hj in this iteration of the simulation, then we count this as a case where the most explanatory hypothesis matches the true hypothesis. And so we count this as a success for that criterion of theory choice, the explanatoriness, fancy E explications of explanatoriness. If HL equals Hj, then we count this as a success for the criteria that would have us always pick out the most probable hypothesis in light of the evidence. We let so you all know, we let n range from 2 to 10 in different instances of this simulation, and any particular instance of the simulation for any fixed n is repeated 1,000,000 times to gauge the success rate, right? The success rate of a particular method. So by the way, of course, at the end of 1,000,000 times, we have some certain number of times with which HK has matched Hj over these iterations. We divide that by 1,000,000, which is the number of times that E has occurred totally, and that gives us the success rate for explanatoriness. Similarly, we have some number of times that HL has equal to Hj over these 1,000,000 iterations that E has occurred, and so we have the success rate for that as well. See how this works? That's the basic setup. Results look like this. So here we have the percentage accuracy, or the success rate is what I've called it too. Success rate as a function of the number of hypotheses. And the blue line is the E explications of explanatoriness. The green line is the posterior probability way of explicating explanatoryness, and purple is chance. So both these methods do better in chance and then random guessing. That's good. That's that'd be bad if that didn't happen. But notice across the board here, the posterior probability, that green line, seems to be the clear winner. Right? If we stopped here, we might think, okay, well, I've used my simulations for concept engineering. I am now going to teach scientists and statisticians using Bayesian methods for theory choice to always just use the posterior probability to pick their pick their favorite theory. Or to favor theories, because it does better than the other option. Okay. However, unfortunately, this simulation is highly inaccurate. It's highly inaccurate because, for one thing, agents priors are assumed here in the setup of our simulations to perfectly match the objective chances of the various hypotheses being true. Remember, how did we pick what the true hypothesis was in our simulation? We just used the prior distribution, which are supposed to be the subjective priors of reasoning agents, and let those stochastically determine what the truth would be. But that's just to assume that agents priors are perfectly accurate. That's completely that's just wrong. I mean, these are not supposed to be, unless there's situations. There could be situations like this where we're applying something like the principle to calibrate our subjective priors. But in general, this is just an inaccurate model. Okay. So how can we change the simulation then to make it more accurate? Well, instead of, just watch how this changes, right? I'm going to highlight in red the changes that I make. So instead here in step 1 of randomly assigning priors, we're going to say what we're actually assigning there randomly are objective chances. Then we're going to add a step. So call this the new step 4, where we assign priors to the hypotheses. We can denote those CR for credence in the various hypotheses. And how do we assign these? We're going to let those be the objective chances plus some X, some error term, where the X is normally distributed around 0 with some standard deviation, sigma. And we can play with that standard deviation. We can play with the sigma to just experiment with different possible degrees to which subjective priors can be inaccurate. And we'll do that. Then finally, in step 6, instead of letting the objective chances, the PR, the probabilities, straightforwardly determine posterior probability, we'll let those posterior probabilities be calculated using the new potentially inaccurate subjective credences. So that's how we alter these simulations to make them more accurate. This is like the part of the engineering process, right? Where we start using a particular AutoCAD design and start simulating using it to gauge efficiency. And then someone comes around and says, look, you got this wrong. This is that you've not modeled this in AutoCAD correctly. This is just not accurate because you got this part of the design wrong. At that point, we'd want to fix the design and then go back to the beginning of our testing of efficiency. That's what we're doing here. If we do it, all of a sudden we get results like this. Okay, now notice this is no longer a function of the number of hypotheses. This is again percentage accuracy or success rate as a function of now sigma, the degree of inaccuracy of our subjective priors. And while likelihoodist reasoning stays constant, because it doesn't, the inaccuracy of our priors doesn't affect it. Of course, the inaccuracy of our priors does affect the accuracy of our posterior probability. It continues to diminish monotonically until we get this crisscrossing effect, where at some point, if our priors are inaccurate enough, indeed, all of a sudden, E becomes the better explication for fruitfulness, for hitting the truth. Here's another result. This is with n equals 10. This is for 10 hypotheses. So at this point, right, you might think, okay, well, this is great. This is really informative because now this informs my conceptual engineering process, because now I can give people specific advice. I can tell them in situations, for example, where you have good reason to suspect that your priors are approximately matching the objective chances, For example, again, if these are situations where the objective chances are not terribly hard to access, you have good evidence, and you've followed a calibration principle by which you've calibrated your subjective priors to make them match the objective chances. In those cases, you should make your theory choice based on the green line, based on posterior probability. But if you're in other situations where you're completely uncertain of the accuracy of your priors, you might then tell people, well, then in that case, you should rather use the explicatum, that is these E measures, which again maps onto likelihoodist reasoning. Okay, so that's useful. That's useful. We're already giving, these computer simulations are allowing us to sort of decipher when different explicata are differently fruitful, and that gives us some good advice to give to those that we want to sort of implement this concept for. However, we could also, so that would be like seeing that we have different layouts in the factory floor, and they have different approximate levels of efficiency that they're going to affect on the factory. And so we say, well, look, it turns out with this process that this floor design would be more efficient, but with this other process, this floor design would be more efficient. And so for different parts of the factory, we're going to implement different floor designs because there's what it takes to optimize efficiency is going to differ in those two areas. That'd be like the move that we just made in terms of explanatoriness and how we explicate it, and the situations in which we advise reasoners to use different explicata. Instead of doing that, though, we might go back to the drawing board. What we might want to do is try to look for theoretical reasons and similarity sort of considerations about the notion of explanatoryness that would allow us to try to sort of cut a middle path in between these two and balance them in such a way that we can have some other formal explicatum that hopefully does better across the board, or at least almost as good, if not better, across the board. And that's what I want to consider now here with the last part of this exploration. So back to the drawing board. Very briefly, here's one way you could try to let theoretical considerations develop, determine a direction through these formal measures, and determine for you a way of trying to sort of balance these two explicata in such a way that you hopefully can get a better result across the board. First, notice that the E's, which amount to likelihoodist reasoning, they, in a sense, place all the evaluative weight on a hypothesis fit with the evidence because they come down to likelihoodist reasoning. Okay, so we might say the E's always give you an advantage for saying more, because if you commit to not just H, but also some H prime, if you say more in your explanation, then there's a really good chance, inevitably, that you can always increase the likelihood. You can bump up the likelihood somewhat by just saying more in your explanation. That's one way to think of what the E's are doing there. So they give all sort of weight to fit with the evidence in terms of likelihoods. What they're not discounting for, what they're not penalizing for, is the fact that every time you say more with your explanation, it might become more and more complex, right? It's not as informationally simple, so to speak. On the other hand, and interestingly, the posterior probability can be thought of in the exact reverse way. So the posterior probability can be thought of as placing all weight on a hypothesis's informational simplicity. And why is that the case? It always penalizes for saying more. You'd never want to say less, or you always want to say less. You never want to say more. Because why is that? Well, because the probability, the posterior probability of a conjunction is always less than or equal to the probability of one of its conjuncts. So even if you get a great boost in likelihood by saying more, it doesn't matter. According to posterior probability, you still wouldn't want to say more. You optimize the posterior probability by saying less. So in one hand, we have informational simplicity completely discounted in favor of evidential fit. And in the other hand, with posterior probabilities, we have evidential fit completely discounted in favor of informational simplicity. And those are sort of two extremes, and that gives us a theoretical way to maybe try to draw a balance between these two. Because after all, remember the goal here for fruitfulness is to hit the truth. And both of these considerations are truth-tropic, are truth-conducive, are alethic. If we want to hit the truth, we don't just want to fit the evidence, but we also want to say as little as possible. Because the more we say, the more chance we have of saying something false. Okay. So how can we cut a middle path between these two? Well, in work recently that I've done, in work that David Glass has done recently, and in old work by I.J. Good, this measure is proposed. This explication, you can think of this as another explication of explanatoryness. That's in fact exactly how Good presents it. So notice, this just is Bayes' theorem, but with less weight, you might say, given to the prior. So with this exponent taken to the half power. If we use that and started, now we want to see how that explicatum works relative to the other two. First thing to notice is that if even in the case where our priors are dead on accurate, right? That's this case where this is that case where I said these are inaccurate simulations because they're assuming that our priors are perfect, that they are the objective chances. Even in that case, you might think, well, here, by discounting the weight that we're giving to the priors, which are, after all, the objective chances, they're totally accurate, we might lose a lot of accuracy in terms of our success rate. Well, no, actually not the case. The red line, which is now the results for the new G measure, sits slightly, very, very slightly below the accuracy of the posterior probability across the board. But both of these effectively do the exact same. They effectively have the same success rates, well above that of the likelihoodist reasoning provided by the E measures. Not only that, but here's where things get cool. If we let our priors be more and more inaccurate, we get these results. So again, we now have the success rates as a function of the inaccuracy of our priors. Notice the red line is, again, the new G measure. Here, at the beginning, we do slightly worse than posterior probabilities. But then we crisscross pretty quickly and start doing better than posterior probabilities. And eventually, the E measures do slightly better, but only slightly. And so the idea here is that the G measure, this new G explicatum, does the best, or very nearly the best, across all situations. There's not a very clear case in which it doesn't do well. And these results from the simulations are completely robust. Here's another situation. That's n equals 10. Here's n equals 5. So again, we have the G measure doing that explicatum, doing slightly worse than the posterior probability, but then you get a quick crisscrossing. And then it ends in the case of very sort of substantial amount of inaccuracy in our priors. Likelihoodist reasoning does slightly better, but only slightly better. So again, this new G explicatum is doing the best or nearly the best in all situations. Now you might think, well, what about, there's deeper uncertainty we could have. There's meta uncertainties, right? There's deeper inaccuracies of our probabilities we could have, because the likelihoods, after all, don't have to be objective. Those can also be subjective. So just to give you one more example of how we can explore certain situations and results using computer simulations here, when we're trying to go for the most fruitful explicatum, let's let priors as well as likelihoods be inaccurate. Then we get this result. And notice you can still describe it the same way. Actually, in this case, there's never a point, and indeed there's never a point even in the limit, where the G measure goes below the E measure. It's always better than likelihoodist reasoning, but you can see it starts off just slightly worse than posterior probability reasoning, and then, but then is superior to all forms of reasoning after that. So again, that qualitative idea that this is the best or nearly the best in all situations in terms of fruitfulness, it again holds true in these cases. Okay, just in conclusion now, let me go through a couple points, just mostly by review. So these simulations can provide powerful estimates of fruitfulness. And notice they're estimates of fruitfulness, not for explicata that we've already sort of paid to implement, right? That we've already put the cost in to implement, but explicata that we're exploring and that we're just experimenting with. These simulations can provide powerful estimates of fruitfulness, at least with respect to explications that seek to improve our performance in attaining epistemic ends. Of course, I am not even close to the only person doing work like this. So just to take a couple of other examples of people doing similar work, especially in social epistemology and using game theory and computer simulations with game theory to try to gauge how fruitful certain explicata are, like group arrangements and group dynamics. Kevin Zollman, Felipe Romero, David Glass, and Igor Duvin are all doing work like this. And there's many others, Kaylin O'Connor, et cetera, et cetera. Okay, these don't merely clarify the normative import of explicata, but they provide important input to the design engineering process itself, right? There's this feedback loop again, as I showed in some of these slides, where we see some interesting results in terms of the fruitfulness of certain potential explicata, and then we might go back to the drawing board and try to design a better explicatum that sort of gets it better across the board, or nearly better. So this experimentation with candidate explicata is not blind and random, but directed by a subtle interplay of background theories, similarity considerations, and et cetera. This is where I showed this on that slide where I talked about goodness of fit or evidential fit versus informational simplicity, and how both are truth tropic, truth conducive. Both these considerations are important to hitting the truth. So if you have two explicata, one of which is extreme on one end and the other one's extreme on the other end, that gives us theoretical reasons for trying to split the difference and try to find and develop and engineer a new explicatum that sort of sits between the two. And this suggests a more nuanced picture of how Carnap's desiderata interact with one another. So it's not just simply fruitfulness takes all, but in the exploration of fruitfulness itself, similarity considerations are important. And finally, all of this is continuous with engineering practices more generally. Concept engineers can truly benefit, I think, by remembering that they are doing engineering in a very real sense. This is not just a sort of image, that, it's not just an analogy, but concept engineers truly are engineers. And so we should use engineering methods to do concept engineering. And it certainly works in these sort of cases, I would argue, as I've argued in this talk. Thank you.